Those of you that know me, I have a saying, I'll go almost anywhere, almost anytime to talk to almost anyone about peat. So let's talk about peat. First of all, let me give some acknowledgments, and I apologize. Whoops. You can only point to one of these screens at once, so I'll pick the close one. I just want to acknowledge that the work I'm going to talk about today has been the work mostly done by people other than myself. So every summer for the past decade or more, we've had 8 to 15 people up here in Alberta, generally based out of Athabasca, and this is just a little picture of the people that do all the work. I'd like to mention Dale Vitt, one of my collaborators. That's me in skinnier form, and Melanie Weil and Kim Scott. So this is our core team. Together we have over 120 years of person-years of experience working in peat in Alberta, which really means that Dale and I are really old and Kim and Melanie are really young. So let's do a little bit of Peatland 101 for those of you that are not particularly familiar with peat bogs. We distinguish two types of peatlands. So peatlands are ecosystems that have at least 30 centimeters of organic soil or peat and are still accumulating peat today. So that's a peatland. We recognize two types, bogs and fens. And so bogs are ambrotrophic. That's a big word. That just means the only input of nutrients and water to bogs is from rainfall and atmospheric deposition. They are relatively isolated from groundwater or surface water inputs. There's not a lot of horizontal water movement in bogs. The water table moves up and water table moves down, but not a lot of horizontal water movement. In contrast, fens are well connected to either surface waters and so receive surface water runoff and may be connected to groundwater as well. In Alberta, there are two different types of fens. Rich fens are relatively high pH, 7 or above. I'm not going to be talking about rich fens. And poor fens, which tend to have pHs closer to 4, like bogs. And so in these fens, the water table tends to be closer to the surface. Water table fluctuation tends to be less than in bogs. So there are two different categories of systems, bogs and fens. They're both peatlands. They're all muskeg. I'm going to be mostly talking about bogs, but I'll talk a little bit about acidic poor fens as well. So this is what it might look like on the landscape. This is so confusing. This is a bog, and so surrounding this bog is a fen. There's a little bit of a fen water track here, and so water is moving from the upland area in the background through this fen and through this fen. And if you were to walk from this fen over into this bog, you would step up in elevation by something like a meter. And so the bog is isolated from these horizontal movements of water, and water drains off of the bog into the fen. In the background, by the way, is the remnants of the House River fire down by Mariana Lakes. Okay, so if you take a look at a bog, sort of as I'm looking out to you, very easy. There's one species of tree, it's black spruce, and in the understory, there are ericaceous shrubs like leatherleaf, Labrador tea, and a few other species as well. If you take an aerial photo from an elevation of about a meter, this is what the bog would look like. And so we see 100% cover of sphagnum mosses, and we see ledum greenlandicum or Labrador tea. There's a cranberry plant, and there's a lingonberry plant as well. And so fairly species poor systems to work with. Okay, so what is supposed to happen, like in the Fort Mac region, when you take these bog systems that have been in this part of Alberta for thousands and thousands of years under a very low nitrogen input regime? So that's the way they persisted for thousands of years. What's supposed to happen when you start adding nitrogen, as is happening in the oil sands region? And so you might view this as our initial working hypothesis when we started this work years and years ago. And we draw this hypothesis from work that's been drawn from researchers mostly in Europe, but also in North America. And so at low nitrogen deposition, before oil sands development, for example, we have, this is a sphagnum moss layer, these are shrubs, that's a tree, in case my graphic art is not obvious. So we have sphagnum net primary production, which is the growth of sphagnum occurring at some level, and nitrogen concentration in sphagnum plants being at some baseline level. As nitrogen deposition increases, let me just say one more thing. For these systems, prior to oil sands development, they also functioned as a net sink for atmospheric CO2. So there's more carbon uptake by photosynthesis than there is by decomposition, and therefore we accumulate carbon as we accumulate peat. So peat is essentially carbon, 50% of peat is carbon. So a net sink for atmospheric CO2. What happens as we start to increase nitrogen deposition? So we get a little bit more nitrogen deposition, and in theory, the growth of sphagnum is supposed to go up. So it was thought that sphagnum growth is nitrogen limited, and because these new nitrogen inputs are being converted into growth, the nitrogen concentration in the sphagnum plants does not change. What happens, or what should happen, is we add more nitrogen in deposition. Eventually, I'll get this right by the end of the talk. This thing is this is like a phaser gun or something. It's never seen one like it before. So as we get more nitrogen, presumably it's become somewhat toxic to sphagnum, and the growth of the plant starts to grow, and they start to accumulate nitrogen in their plant tissues. As we add more nitrogen, you really start to knock off the growth of sphagnum because it's accumulated all the nitrogen in its tissues as it can. At this point, it was thought that nitrogen moves down, ammonium and nitrate coming in rainfall, moves down into the peat profile. And as a result, we get greater shrub growth. So that's indicating greater shrub growth. At some point, when you get this greater shrub growth, you shade out the sphagnum mosses, and so I've shown the sphagnum layer as red, meaning dead. So red is dead. So if you get to this point where ammonium and nitrate coming in rainfall is percolating into the peat, shrubs have proliferated and shaded out the sphagnum mosses, then you get obviously sphagnum growth and nitrogen concentrations go to zero. And at this point, in theory, because there's no photosynthesis by the dead sphagnum, the fixation of CO2 goes down and the release of CO2 goes up, and the bogs in the oil sands administrative area would shift to a source of CO2, not a sink. So that's the conceptual model that we went into our work with. Okay. So how important are bogs and fens on the landscape? This is from a paper that just came out a month ago in ES&T. So we've taken the Alberta wetlands inventory and just applied GIS techniques to I'll get this right by the end of the talk. Back, okay. So we've looked at 3 different areas, the entire oil sands administrative area. This is a square sampling grid that I'll talk about from a synoptic survey that we conducted a while ago. And this octagonal or rectangle, whatever this is, multi-agonal polygonal figure is a sampling grid defined by the outermost sampling points of a synoptic survey that we did in 2013. And so the point of this is, if you put all this together, it depends on where you look, but in general in this region, bogs cover 6 to 10% of the landscape and fens cover 21 to 53%. So a large percent of the landscape in the Fort McMurray area is either bog or fen. Furthermore, these peatlands are well distributed throughout the oil sands region. So at least within this 80 by 80 kilometer grid, you can find bogs or fens in every direction. And also, I would be remiss not to mention that peatlands have extreme importance to our First Nations community members, as we've heard about earlier in the presentations today. So that's why peatlands are important. In addition, bogs especially, but to some extent poor fens, were expected to respond to increasing nitrogen deposition. So let's look a little bit about wet deposition of nitrogen and sulfur, and I'll show you a little bit of data. So these are bog sampling sites that we have as part of our intensive bog monitoring program that we began in 2009 with support from WBIA. And at each of these sites, We have these ion exchange resin collectors that I'm not going to go into tremendous detail. These are the same types of collectors that Mark Fenn has used in his research in the oil sands area. At each of our intensive monitoring sites, we have several of these. And so we have 12 of these at each site. We have 5 sites. We had 7 collections up until 2012 when our WABIA funding ended, although my group has continued sampling in this intensive bog monitoring effort since 2012 using funds that we have available to us at Villanova University. And so that's how we collect the precipitation. And we made an effort to gather all of the resin deposition data that we could find historically anywhere in the Fort McMurray region, and these are maps of all those sampling locations, to put together these 2 maps. And so these are maps of wet deposition of ammonium plus nitrate and of sulfate in the oil sands region, and as you can see, there are clear gradients of increasing nitrogen and sulfur deposition as you get closer to the industrial center. This, of course, everyone recognizes as the footprint of the oil sands activity north of Fort McMurray. So we clearly have gradients in nitrogen and sulfur deposition. Okay, so the first question is the growth of Sphagnum fuscum, the dominant peat-forming moss in bogs, increased by nitrogen deposition? Because this is what we would have expected when we began several years ago based on a European model. The way we measure this is very sophisticated. There's a Sharpie for scale, and that's a steel wire. You put these steel wires in the ground in the peat in the beginning of the year and measure how much sticks out. Come back in October, and less is sticking out because the moss grew, and so you get vertical growth of the moss. If you know the bulk density of the peat, then you can get annual net primary production. We have thousands and thousands of steel wires in peat in the Fort McMurray region. And so the question was, is Sphagnum fuscum growth stimulated by elevated end deposition rather than show you complicated data graphs? Here's the answer, no. The answer was no when we published a paper in 2010. The answer was no when we published another paper in 2014. We are indefatigable in our efforts to answer this question. The answer was no in 2016 in a paper we just published last month. We have an ongoing NSF-supported project where the answer is no. And so this is not what we expected, but sphagnum growth is not elevated by increasing end deposition. Why not? Why were we wrong? And I'll just mention very quickly, one of the things we found is that it's not deposition, but nitrogen fixation, which is the major input of nitrogen to bogs in northern Alberta. So this was published in 2014, and whether you look at this on a species basis, or these are 4 of our intensive monitoring sites, these are the rates of nitrogen fixation, which are 20 to 40 kilograms per hectare per year, whereas nitrogen deposition and rainfall would be way down here. And so that was a new finding from our work. Okay, I want to look a little bit at plant tissue chemistry because another potential response of increasing nitrogen deposition should stimulate growth, and after you've stimulated growth, plants take up excess nitrogen into their plant tissues. And so we've looked at these 12, I'll get it right by the end of the talk, these 12 species, 2 lichens, vascular plants, these are various vascular plants, and 4 sphagnum species to look at nitrogen and sulfur concentrations in their tissues. In particular, to ask the question, do plants or lichens respond to elevated deposition by increasing N and S concentrations in their tissues? And so again, this is from our synoptic survey, sampling over 2 days in 2013, where we've already shown there to be gradients in nitrogen sulfur deposition. This is nitrogen at the top and sulfur at the bottom. Evernia is one of the lichens, and Cladonia is another lichen, and you see clear gradients of increasing concentrations of nitrogen and sulfur in the lichen tissues as you move closer to the industrial center. Okay, this is the same sort of thing, looking at 2 different species. This is Ledum greenlandicum or rhododendron greenlandicum and black spruce, Picea mariana, nitrogen and sulfur also seem to show some gradients of increasing concentrations in tissues as you move closer to the industrial center. Sphagnum, by the way, does not show this response. Okay. So that's from the synoptic survey. We wanted to look also within a site, how do nitrogen and sulfur concentrations in plant tissues change over time? So we call this intensive sampling. We began this in 2009 and have continued it through 2016. We have collected approximately 10,000 plant and lichen tissue samples to be analyzed for carbon, nitrogen, and sulfur. And so this is what it looks like. Now, you don't expect there will be no quiz, so you don't need to know the details. But to me, this is what monitoring looks like. So we began in 2009 and have continued through 2014. We actually have samples for 2015 and 2016, but we haven't analyzed them yet. And so these are from our 5 intensive monitoring bog sites over time, nitrogen at the top and sulfur at the bottom. And so the point is here is to reveal any long-term trends that might be happening. You need this kind of intensive data collection. Okay, so, and this is what happens with Evernia. There are some clear patterns that as you get closer to the industrial center, there's more nitrogen, there's more sulfur. You might actually squint and see, it looks like there might be a long-term trend of decreasing sulfur concentrations in Evernia. It takes long-term monitoring to reveal this kind of thing. So that's for one of the lichens. I'm not going to show you all the species. This is the same pattern for black spruce. And so you see it's a very different pattern because black spruce has this pulse of nitrogen and pulse of sulfur in the newly formed needles at the beginning of the growing season. And so that's kind of interesting, but it tells us from a monitoring perspective, you really don't want to be sampling at this time of year because you're confounded by plant physiology. And so the best time to sample really is midsummer, not early or late in the growing season. So we've learned that. I want to show you 2 more. One is for Sphagnum fuscum, the dominant moss, and I want you to focus on nitrogen. Just again, squinting or blurring your eyes, it kind of looks like nitrogen concentrations went up and then flattened out. Okay? And so this is the kind of long-term pattern that may or may not be a response to changing nitrogen deposition. We see the same pattern for one of the vaccinium, the small cranberry. Nitrogen seems to go up and then level off. And so what happens to this in the future, only further monitoring will reveal. I'm going to skip these and just answer 2 more questions. Is bog porewater chemistry affected? So if things are really bad and nitrogen is moving down into the bog porewater, then we're at the late stages of saturation. And so we've measured a lot of water chemistry, and the answers are no. I can back up. There's no evidence that increasing nitrogen, ammonium and nitrate, and increasing sulfate is making it down to the bog water table, or peatlands are really good at taking up and storing ammonium and nitrate. Okay. Is there a shrub response? And so this is one of the things that's supposed to happen when you add more nitrogen as you get more shrub growth. And I'm not going to show you detailed data, but we've looked at this using these handheld reflectometers that measure the reflectance of photosynthetically active radiation and other radiation from vegetation. And the answer to this question is yes, in a bog and a poor fen, yes, in bogs, and possibly in our Wabia sites. And so it looks like we're seeing elevated shrub growth. Now, I'm almost finished, Dan, not to worry. This is our study formerly funded by SEMA, where we're experimentally adding nitrogen to plots in a very complicated way. And so these are some of our plots showing us raining nitrogen-rich water onto a poor fen in a bog. And this might be clearer on the darker one over there. This is a 0, 5, 10, 15, 20, 25 kilogram per hectare per year nitrogen addition plot, seen from a drone from one of our students that put up there. And as you can see, looking at this, as you get to the 20 and 25 kilogram per hectare per year plots, there's a lot more shrubs. And this is a response after only 5 years. And in fact, if you look at this even more carefully, you can start to see an increase in shrub growth at the 5 and 10 kilogram per hectare per year. So it looks like we do have increasing shrub growth. I'm going to skip that, and I'm going to probably end with this. This is where we might be headed. And so as we continue to have increased nitrogen deposition as wet ammonium and wet nitrate deposition, it looks like we are headed toward this, a scenario whereby we have stimulated the growth of shrubs, which is clearly evident both in data and the picture I just showed you. That growth of shrubs has shaded out the sphagnum, and so sphagnum actually will die off. We have movement of ammonium and nitrate down into the porewater, and the systems turn from a sink of atmospheric CO2 to a source of atmospheric CO2. And so, based on the data we have so far from monitoring and from research, this is where we might be headed. Whether or not this is going to happen requires further study. Every scientist says this, we need more study. But I think what this begs for is the need for long-term monitoring at individual sites with multiple sampling dates throughout the growing season to be able to tell how far along we are toward this not very optimistic future potential scenario.